Afternoon. My name is Kaur. I'm a researcher here at the Institute of Computer Science, and welcome to today's data science seminar, Data Engineering, the unglamorous reality behind data science. So the plan today here is that me and Riccardo, a colleague from here, will give a short introduction to what we mean by data engineering and what is the work that we're doing here at the Institute of Computer Science, and kind of what are the open challenges in this area. And then we move on to 4 excellent speakers from 4 different companies afterwards. And Riccardo, the floor is yours. Thank you, Kaur.
Good afternoon. My name is Riccardo Tommasini, and I'm an assistant professor here at the University of Tartu. I got my PhD from Milano in Italy, Politecnico University, on a thesis on the web and the data around it we call velocity on the web. During this presentation, I will mention a bit about it. Most importantly, here in Tartu, I am a lecturer of data engineering, and I'm also part of a member of the data system group, which is the group that here at the university focuses on big data, artificial intelligence, distributed artificial intelligence. We do many things from graph processing to real-time analytics, from explainability to automated machine learning. And I've been trying to explain this before, and this is a real world whiteboard and me trying to give a clue of what we do. And this is how I feel when I try to do it. So it's really like too many things to think about. So I try to be more visual this time, and let's start with big data, right? So if you come from the world of big data, you probably have heard about the 3 V's: volume, variety, and velocity. Volume is about the amount of data you have. Variety is the amount of the different kind of data you have. And velocity is how fast the data arrive and how fast you want the insights to be produced. Now, if you are in the big data loop for a while, and you probably have seen this V growing, and this is like a rough trend on how the V's are going on in the years. They have a veracity coming over, volume, value, stuff like this. But let's stick for the 3 ones for now. Okay, just to keep it simple. The people in my group, the researchers that work with me, are positioning around this 3 V's. Ahmed Awad, which is the head of the group, focuses on velocity and volume mostly. Radwa El-Shawi focuses on machine learning, so I will position here between variety and volume since we try to distribute the workloads most of the time. Then myself and Feras Aweshesh, which is a postdoc in the group, we try to stick with data variety and velocity simultaneously, as well as volume by the means of cloud computing. Another important thing in the group is AI, as I mentioned just now. And I like this picture about what are the needs in AI, because they will bring us at a certain point to the world of data engineering. As you can see, like the core AI, the one everybody talks about, the AI is on the top and is much smaller. Most of the work in this context focuses on testing, experimentation, then even more on analytics, further more on cleaning and anomaly detection, going back to creating reliable data pipelines and instrumentation techniques for getting the data in. So the same people I just mentioned, like Ahmed Awad, the head of the group, position itself between analytics and data cleaning with business process modeling. While Radwa El-Shawi sticks on top. She does core deep learning and explainability. Myself and the Feraz are at the bottom in the pipeline, and that's why I'm here today. We try to stick with preparing data pipelines, making work mostly in streaming, and we take a bit of a clue of what the cloud does to make this work, to make this workload scale out for production-ready systems. We don't work alone. We have PhD students and master students. I here put the 6 PhD students and a future PhD students in our group. From the top left, we have Asko Seba, Hassan El-Sarib, Samuel Langhi, Javad Bahamani, Carlos Ramos, and Mohamed Ragab. Just want to mention them because they are actively member of our group and they deserve it. We also have some teaching activity in the group, and our teaching activities focus on 3 areas mostly. We have data engineering as a core teaching activities for this fall semester. And then in the spring semester, we have advanced databases and big data management. These two courses go deeper in the aspect that I just mentioned, focusing on technology that you can use for analytics at scale, as well as what power the internals of our databases nowadays. But let's stick for data engineering. So how does data engineering position comparing to the AI hierarchy of needs? Well, in my opinion, is in somewhere in between, right? It's just above cleaning and anomaly detection. But let me give you a concrete idea of what I think data engineering is. So I think this tweet captured very well the idea. So let's have a data scientist asking me, can you just quickly pull data for me? Sure, no problem. Just let me start from this ideal table you think exists. Now free meal, gentlemen. We have to prepare this data for you. And most of the data science projects fail because data are not available. So data engineering is important, and that's the bottom of the pyramid that sustains everything that's on top. Without this part of the work, data science is not even possible. I also like this quote by Gordon Lansing-Legg, which says that a scientist, in this case data scientist, can discover a new star, but cannot make one. It takes an engineer to make a new star. So I hope I gave you an overview of what I think data engineering is, but actually that's a trend that is debated by the community as a whole. A couple of years ago, this post, The Rise of the Data Engineer, came out, and I think it's pretty cool in identifying what are the characteristics. He's a specialist, he's a technical person, data engineer, which tries to identify and maintain data available. It's set to operate data infrastructure, the entire data infrastructure. So he has to know a little bit of cloud, a little bit of programming languages, a little bit of data systems. He also has to speak with people that come from business and with data scientists too. So he cannot, data engineer must not give for granted communication, and it's not just technical, it's also people work. More practically, it's a combination of skills. It has to know a bit of what data scientists do. It has to know a bit what software engineering do, but it's also a peculiar work which builds on top of years of skills in data warehousing, ETL, and database design. But nowadays, data are changing. They're not changing just in terms of the 3 V's of big data. They come all at the same time. We have variety, we have volume, and we have velocity all together. For instance, this is what happens in 60 seconds on the web. The amount of information produced every moment is, it's crazy. And many challenges are faced nowadays to prepare a pipeline that doesn't just scale to process this data, but do that in real time. Because more and more often, we need to deal with the insights that are required right now. That's the moment where we have to take the decision. The more we wait, the less important the less impactful our decisions are. So we cannot skip the real-time aspect. We cannot skip the variety aspect anymore. And as you'll see today also, another important aspect is data discovery. So it's important to identify the right data sources in order to make the right decisions. And that's a problem itself. In such an abundance of data around, what are the right data that you need? What are those that power your decision better? And what is just noise? The trend is growing, and data catalogs are probably the 2020 thing in the area. Dataset search is Google's attempt to create data catalog. And I think today you'll see other attempts to make this data discovery a thing, and how to engineer data sets in a way that are productive for your data science pipeline. That's all for me, and I'll let you continue the rest of the webinar with Kaur. So here you go.
Thank you. So when Riccardo gave us a very good introduction about the data engineering from the data infrastructure and cleaning side, I'd like to talk about another aspect that's maybe often neglected, often not considered part of data engineering, but I think actually will be very strongly represented from the company side today, which is data set engineering. So first, a few words about me. I did my PhD in computational biology at the University of Cambridge in 2017. And since then, I've been a kind of researcher and a group leader here at the Institute of Computer Science. My area is bioinformatics, so we're also teaching a course in bioinformatics. But today, kind of, when people ask what I am or who I am, I'd like to say that I'm a biologist first, because I answer biological questions. I'm interested in biological questions. I'm also a proud research parasite because I don't generate my own data. I take data from other people, from other labs, collect it and reanalyze it, discover new things. And so the term research parasite comes from a prominent medical journal. Had an editorial a couple of years ago where they denounced people like me who use another group's data for their own ends, possibly stealing from the research project planned by the data gatherers, or even use the data to try to disprove what the original investigators had posited. Fortunately, this is kind of a minority thinking in the field, and I think especially in my area, which is human genetics and genomics, data sharing is very much a norm, and so there's also kind of reaction to this. Kind of computational biologists devised the prize, which is called the Parasite Awards, celebrating rigorous secondary data analysis. So one of the bigger projects, the biggest project that we're working on right now is an EQTL catalog, which is kind of our largest parasitic project to date. I'm not going to do in the detail about the project. It's basically like a large biological database where we collected data from different cell types and tissues from humans. So we have over 21,000 samples. A sample here is basically anytime we take like a piece of a skin or other tissue from somebody and then we process it, it's a sample. So there's basically 21,000 times somebody has collected some actually material from living or often dead person. And it's from 5,700 individuals, and it's kind of, we collected data from over 21 individual studies. And the raw data is about 200 terabytes. It sounds large, but actually for us, kind of the data volume is not an issue. What's bigger issue is kind of the data annotation and data kind of quality. And there's a big team behind this project. So Nurlan is a PhD student in my team here, and Katerina is a software engineering doing a lot of work for this project. And then we have collaborators as well from the European Bioinformatics Institute. But yeah, for us, kind of the issue is data quality. So many of you have seen this quote hundreds of times from Anna Karenina, that all happy families are alike, each unhappy family is unhappy in its own way. My feeling is that all clean datasets are alike, each messy dataset is messy in its own way. And what I mean by this is we often, when we get this data from these 21 different studies, we often have missing metadata. We don't know kind of which samples match to which individuals, which cell types have been profiled and so on. Sometimes the metadata is there, but it's incorrect. Sometimes kind of there are low quality samples that we want to get rid of, but we don't know which ones they are. There's contamination issues. There are cryptic data formats. There's like at least 10 different ways of sharing genetic data from individuals. And then there's kind of other kind of data being split and between different files, directories, repositories. It's kind of the real kind of bottleneck is kind of getting all of this data together and making sense of what the metadata is. And then the processing is something that we can automate quite well. So where does it come from? The issue, like one issue is in one of the datasets that we were working with, we had an issue where I think 145 samples were swapped. So they were like, the IDs were kind of randomly swapped between individuals. We were kind of struggling to know what was going on. Fortunately, we could figure it out that there was a problem. We still don't know what exactly happened, but my best guess is that biological samples are often handled in these 96-well plates. So you have rows and columns, and if you turn it like 180 degrees, it's still a 96-well plate. So I think what happened is that somebody turned the plate and then all of the samples were completely wrong. So fortunately, we can catch many of these issues with like internal consistency checks. And there's kind of lots of kind of background knowledge. We can catch many of these things. Like we can look at like plots and see for outliers in there, or we can look at other types of data. We can kind of catch many of these things, but this work is manual and it's very tedious. So we kind of get the data and then we start making sense of the metadata. I think we're getting really good at it. So now I think it only takes like 3 or 4 days per data set. And then after that, kind of processing the data itself is maybe like a couple of hours of actually manual intervention. So it's the quality control that's really challenging for us. And kind of what's challenging is not actually kind of figuring out, well, some of this is challenging what is figuring out what the issues are, but I think a bigger issue is that that as a human being, I can very quickly judge that there's this issue, we should fix this. But then I have to go to some text files and actually change the IDs or go to like some Git repository and fix these issues. So it's, you can kind of, I look at the data, it's obvious that there's this issue, we should kind of fix this sample. And then I spend like 5 minutes writing code to fix this particular issue. So it's a kind of, there's a very strong friction from knowing what's wrong to actually kind of coding it in a way that we've now fixed this and also being able to kind of track what they've changed. So, kind of that's, I think, where, so it's the kind of this converting judgments about data to actual annotations. So you could think about like when you're writing, that you were writing, we really lack good tools for that. So you could think about like you're trying to write enterprise software in Notepad. You know what you want to do, but it's really tedious to actually get it done. So that's kind of where I leave with the problem statement. And I think now we'll go to the 4 presentations from the companies. First up is Łukasz from Bolt, talking about their data platform. Łukasz, the floor is yours. And if you have any questions, write in the chat. I will ask them at the end of the presentation.
Thank you. Hello, everyone. My name is Łukasz Grądzki. Today, I'm going to tell you the story about data platform that we built at Bolt, and also the lessons that we learned from scaling data infrastructure in a hyper-growth company. Let's start from who am I? I'm leading data engineering team at Bolt. I joined the company 3 years ago, and because of that, I had the chance to participate in almost all the stages of building data platform at Bolt. Before Bolt, I was working in another company called Shadow Cloud, where I had the chance to gain experience in building distributed systems that are also optimized for processing high volumes of data. Did you know that transportation is the second expense, the highest expense for households in Europe? In most of the cases, for some families, it will be cheaper to use on-demand transportation instead of having their own car. This is the problem that Bolt tries to solve. We are the leading European on-demand transportation platform that is focused on making urban travel easier, quicker, and more reliable. So for the past 3 years, I had a chance to see how the company grows and how it changes over time. So our monthly number of passengers grew from 3 million to over 30 million. The number of employees also increased to almost over 1,800 all around the world. We expanded our business to over 35 countries and over 150 cities. You know that our main business is ride hailing, but also we open new business lines. One of them is Bolt Food, that is aiming for delivery of food, but during the COVID times, it's not only the food, we're also delivering other kind of goods. And also we expanded towards micro mobility in the cities. We launched in several cities the electric scooters and also electric bikes. So you may ask, what is the difference between Bolt and other competitors? Basically, we do more with less. You can see here on this graph the amount of capital that was raised by different companies in the transportation industry. Uber had to raise over $25 billion to build over $50 billion business. And here on the other side of the scale, we have this small guy called Bolt that raised just 30 million to build a business that nowadays is estimated to be somewhere between around $1.7 billion. So you can see the business is growing, and it's a very challenging thing also for the data engineering team that has to somehow keep up with the increasing amount of data. So today I'm going to tell you a bit more about how we set up our initial data warehouse, how it evolved over time, and what are the things that we learned on the way. So it's important to state that Bolt is a data-driven company. It means that there are very many different teams that need access to data. First of all, we have local operation teams in different countries that need to know what is the current situation in their cities. We have data analysts, currently over 30 of them, who build dashboards, who generate reports. We have also data scientists who try to automate the systems to make decisions. The product teams need access to data to make educative decisions about the features that we are going to launch. And also we have automated decision systems, meaning that all the models that are developed by our data scientists team also need access to data to train the models and also to serve them in production environment. This is the graph that represents symbolically the amount of data that we need to process since we started our operations. It was in 2013. And you will see it a few times over my presentation. So let's start our journey from some point in past, like 4 years ago, what we had at the very beginning. So at the very beginning, we are running our reporting infrastructure directly on the operational databases. I mean, back in the days, it was a MariaDB, and we're running our aggregated reporting queries directly on the database, as bad as it sounds. It was okay at the very beginning, but over time, unfortunately, as the amount of data was growing, we started experiencing some performance issues. The databases were split into several shards, meaning that sometimes the joins were not possible between different shards. That was quite challenging. We had to do something about it. So we decided to go with initial data warehouse setup. So right now, the amount of data increases. We are somewhere in 2017. And yeah, we have our production databases. We have our reporting, what stands in between those two things. Most of our infrastructure is based on Amazon Web Services. So for us, it was quite a natural choice to go with Amazon Redshift to accomplish this task. However, the data has to somehow reach the data warehouse. For this purpose, we had to build a proper data replication system. Amazon Redshift depends on some other service from AWS called Amazon S3. It's a service for storing objects. So firstly, the data has to land in Amazon S3 to be later synchronized to Amazon Redshift. So for this purpose, we have set up custom replication mechanism to replicate data from MariaDB shards, but also from the backend services written in Node.js. And then there was another process that was orchestrating data ingestion to Redshift. And obviously, Redshift became the source of truth and the main source for generating our aggregated data and reports. So a few words about Amazon Redshift. It's based on PostgreSQL, but it's not PostgreSQL, meaning that it just offers the same interface, but underneath it's a completely different concept. It uses a columnar storage. Later, I will tell a bit more about it. Some functions are not available or work differently in comparison to PostgreSQL, so it's better to read the documentation before you use it. As it's columnar storage, it supports very good, very efficient columns compression, and it's very scalable, meaning that if you need more compute power or storage, you just add new nodes. For us, it became, once again, a unique source of truth, and all those features make it a very good solution for serving aggregated queries. So those queries when you want to count the number of rows for a particular period of time or calculate some average values. A few words about row and columnar store. So in most of the traditional relational databases, a particular row of data, a record, its properties are stored in consecutive cells in memory, meaning that it's very cheap to retrieve a particular record. But if you want to make aggregated query, the software has to skip several addresses in memory. So it's not very efficient. Here it comes a columnar storage that tries to solve this problem. So instead of storing just the entire records as a consecutive memory, it stores consecutive values from a column as adjacent cells in memory, meaning that it's very efficient to scan huge amounts of data from a single column and then calculate aggregates on top of it. However, our initial setup had some limitations. So first of all, believe me that when the business grows fast, the data behind it grows even faster. And as I said, it's very easy to add new nodes to Redshift, but it also means that the costs are proportional to the data size. So at some point, we became those two guys who were burning money just to keep our data infrastructure alive. Also, we had several other issues related mostly with data quality. As I mentioned, we had very custom replication pipelines, meaning that whenever the schema has changed in some source database, we had to manually modify all the pipeline along and propagate this change. And over time, it was very expensive from the operational point of view to handle those changes. And it was very buggy. So if your team is not the expert of the low level, that has the low level knowledge of the databases that you use, it's difficult to discover possible corner cases before you develop all the software. Also, over time, it was the first very fast approach for developing data infrastructure, meaning that we started also facing some query performance issues. And we noticed that as the data team grows, we have more data analysts, data scientists, different people try to use different queries to define the same features and properties. And at some moment, it may mean that, yeah, two different queries give you the same results, but most of the cases, it wasn't the case. So we had to also somehow standardize it. But also from this initial setup, there were some lessons that we learned. First of all, maybe it sounds very trivial, but use tools that are tailored to specific tasks. It means that if your relational operational databases are not the best choice if you want to have some aggregated queries. Also, it's very helpful to identify types of the data that you have in the system. There can be data that is mutable, meaning that the particular data record can receive updates over time, and some pieces of data that are immutable, meaning that it's a kind of event data that happens and it cannot be modified later. So those two data sets should be treated in a bit different way if you want to optimize it for performance and costs. As I mentioned, mutable data, unfortunately, it's very tricky to handle it. It changes. So if you replicate it in several stages, it may happen that different elements of your system have different version of the data. And also it means that it's very expensive and bug prone. So wherever you can do it, try to avoid it, at least on the data infrastructure. And maybe the last thing here, try to identify access patterns. So with time, you will learn that your users need some data sets more often, whereas the other data sets are accessed maybe just once a month just to debug some things. So it's important to identify those two sets. So how we, after these learnings, how we approached the problem and evolved our infrastructure. We had to scale somehow Amazon Redshift. Fortunately, Redshift offers an extension called Amazon Redshift Spectrum that basically, instead of copying the data from S3 to the main Redshift cluster, if the data is structured in a proper way in S3, it's possible to query SQL, to launch SQL queries directly on this data through Spectrum. So another good advantage of that is that we pay per query amount of data that we scan, and it's not necessary to have a very big cluster just in case you want to query this data. So it's like another optimization here. And as Amazon S3 is immutable data store, meaning that if you want to update existing piece of data, you have to download the file, update it, and upload it, meaning that you don't want to update data in S3. It's ideal for append-only event-like data. And the biggest advantage that comes here are the storage costs per 1 terabyte of data. So if you compare Redshift and S3, depending obviously of what is your configuration of the Redshift cluster, S3 can be up to 90 times cheaper than Redshift. Sounds like a perfect solution, right? Well, unfortunately, nothing is for free. You pay per data that you scan, and it means that if you have very frequent queries to this data that is stored in S3, it can become a bit expensive over time. So be careful there, you don't want to burn money. And also we had to optimize this part too. So how the data can be stored in an efficient way in S3 if you want to query it in place. We decided to go with the Parquet file format. Basically, it's a column-oriented format, very similar in its structure to how Redshift stores the data internally. And also it supports different types of encoding and compression. So it's very efficient to store huge amounts of data and later to query it. And yeah, the pictures may look very simple. You have data in S3 in Parquet format, and you can query it from Amazon Redshift using Spectrum. Well, it's not so easy. To get the data to Parquet, you would like to have the data grouped into bigger batches. And in our case, the raw data was gathered in the JSON format. We had to somehow convert it to Parquet. And for this purpose, we have developed an infrastructure with Apache Spark, and that is orchestrated using Apache Airflow. So that all the setup for different tables was producing the data that originally was stored in JSON and later was converted to Parquet format. As I mentioned, we had also troubles with data quality. Handling mutable data is especially tricky here. So initially we had cron-like processes that were trying to capture just the change of the data since the last time it was synchronized to S3. It was very, very prone to errors, very buggy. But fortunately, there are better, more mature solutions in the market available. We decided for this purpose to go with Apache Kafka. It's an open source messaging system developed in LinkedIn. It has very high throughput, it's horizontally scalable, and it offers very different connectors for consuming data and also writing data to different systems. In our case, it was very important because we needed to get the mutable data from MariaDB to Kafka and then from Kafka to S3. For this purpose, we are using the connector for this from the Debezium package. So how did the infrastructure evolved over time? This is the initial picture of how it was with the initial data warehouse setup. Now we are in 2020. The amount of data is much bigger than what we had initially. And also there is a higher demand from the data users to get access to data. So over this time, the size of our data science and data analytics team increased. There are much more queries from those analysts. We have advanced A/B testing infrastructure that it means that we need to have results of different A/B tests of different when we test different features for product teams and so on. And also data scientists produce quite many models, and we have to develop the infrastructure to train them and to deploy them into production. So in our case, it's also AWS Stack, Amazon SageMaker for training and serving models. And that put a lot of pressure on our data infrastructure. So I mentioned the several technologies before. I'm going to put them here in the picture so that you can see it on the high level. Kafka replaced our custom replication pipeline and made our mutable data more reliable. We also added Spectrum to the layer of Redshift, and we added Spark and Airflow for converting different data formats to have, especially for the immutable data. So even this stage gave us some new lessons that we learned. First of all, data quality is a continuous battle, meaning you cannot leave it for later, or if you do it, then it's going to bite you very badly afterwards. This is like the constant thing. It's like tests in software. You have to have them from the very beginning if you want to avoid problems in the later stages. In our particular case, we discovered that semantic quality checks should be built into processing pipelines. So sometimes we have cross-validation of different sets. For example, when we ingest data for, let's say, number of writes in the particular geographical region, we would like to validate it, for example, against the number of invoices that we have launched so that those numbers match. And that makes like an additional testing here. Traditional Pareto rule applies here too. So when you have so many different ideas how to improve your infrastructure, you know, it's not a revolution, it's usually an evolution. Try to identify those who bring you the biggest value and focus on them, because usually they will bring you the biggest value. And as your organization grows, focus on workshops and documentation to educate your users, meaning that if they have access to the proper materials, you don't have to devote so much time to provide support and guide them through the system. And yeah, there are also bonus learning. Probably you know that recently we had some bad virus going around the world, making some mess with people's lives and people's businesses. In case of Bolt, it was also a small bumper on the road. And from this, we also had to learn a bit. So it means that your business grows fast, but it's not going to be always like this. The environment, the markets change. In this case, there can be like those unexpected circumstances. And sometimes it's necessary to adapt as data engineering team and scale your infrastructure down. So what it means that when you design your infrastructure, be ready to scale it also down in the future. So when you have to make different types of decisions about the features that you want to implement, try to keep in mind things like, what if we can separate storage and compute? What if, so that they can scale independently? What about data retention? What about the data sets that you store? Maybe some of them are expensive to store and you don't need them at all. And also in case if your infrastructure is hosted in the cloud, the cloud providers, they like to give you discounts for long-term commitments. Be careful, that can be a trap in case you have to scale down your infrastructure at some moment. So I would say that this is those are the most important learnings that we got throughout all the journey. Let me just repeat them so that it stays here with you. Remember to use correct tools for the tasks that you want to perform. Try to identify access patterns to your data. Mutable data is very tricky. It's expensive and bug prone. So when you design your systems, try to go with some event-like collection system. Data quality, it's very important. Don't leave it for later. Focus on 2080 and iterate, and prepare proper materials for your users so that they can learn themselves how to use your infrastructure. And keep it frugal. Be ready to scale down your infrastructure. And thank you very much for your attention. I hope that you enjoyed this ride. If you want to have questions after this presentation, I leave you here my email and Twitter handler. And did I mention that the company grows? So in case you consider developing your career with Bolt, check out this QR code. Maybe you will find some good opportunity for yourself. Thank you very much.
No questions. You can't let go away. So there was one question which I think you might have answered already. There was a question about so what tech stack did you use to move data from MariaDB to S3, and could you have used like this Amazon database migration services for that?
Okay.
I think you kind of answered in the end. This came in the beginning before you mentioned Kafka.
Yes. So. Okay. So most of our backend stack is hosted in AWS, but we use Node.js for that. So I would have to say that initially data engineering team evolved kind of from the backend teams, and we developed very custom cron-like scripts in Node.js that were just querying databases, since like some watermarks that we had there, trying to figure out what are the new rows that appeared or which rows were updated, and pushing the data to S3. And I can say that Node.js is not the optimal technology for processing huge amounts of data.
Another question that I'd like to ask is, you really stressed kind of the importance of checking data quality. Is this something that you knew 3 years ago, or this is something that you've now learned that you should have started looking at data quality earlier?
Well, this is the session about learning. So unfortunately, we had to learn it the hard way. And very often, if the organization grows and you have different people developing services that produce the data, later you have data engineering team that tries to move this data to the data lake. And then you have data scientists trying to figure out what this data mean. Well, it can get complicated over time. So that's why it's very important to keep it in mind from the very beginning.
Thanks. And the kind of one other thing that I noticed is that that you're like that I like the distinction between kind of mutable data and immutable data, and kind of it seems that like for immutable data you can basically get away with like indexed binary files like the Parquet format, or I mean there are other formats as well that you seems that kind of what you gravitated towards is basically having like indexed binary files in stores that you can access.
Yes.
It's kind of what kind of which is kind of nice because that's what we've ended up doing with our databases. The other thing, kind of like, where do you kind of draw the line in terms of like how many queries do you need to be able to like that you would move it to Redshift so that the S3 would be too expensive? Or do you have like ballpark estimates?
I think that if you have a proper monitoring of your setup, both from the well, in this case it's Redshift and Spectrum, but basically in the end everything can be translated to the invoice that you receive at the end of the month. So if those metrics show you that some of the access patterns have changed and the things that were meant from the very beginning to be this cold storage stored in S3 and queried there in place, suddenly the costs go up, that means that you have to react. But I think it's very difficult to have a very clear rule here. I think it depends on each use case. In our case, we decided to go with Parquet, but I imagine that if someone has to process, for example, documents data or more unstructured data, then they will have different means to measure it. So I think there is no clear answer to it.
Okay, thanks. And I think the final question is from the chat. What is the difference between columnar stores versus wide column stores?
White column stores.
They say white column stores. I don't know.
Okay. I'm trying to.
I don't know what the question means. So.
Yeah. Okay. I also don't understand it completely, but I will assume that white columns store means something like text type in the databases, meaning that you can have a big binary blob stored as a value in a column.
There's a classification that Cassandra is an example of white column store or HBase.
Okay, I have to admit I have no experience with Cassandra, so
okay.
I wouldn't be able to answer this question, unfortunately.
Okay, thank you. Thanks a lot for a really great presentation. And next up we have Kristjan Eljand from Eesti Energia talking about labeling the unlabeled. There was also a very long additional title, but I don't remember it.
So hello guys, my name is Kristjan. I work in Eesti Energia as a technology scout. Day-to-day work includes finding predictive and prescriptive analytics business cases in Eesti Energia and applications. Today I'm going to talk to you about one specific case of predictive analytics and the challenges that we faced with annotating the data. But first things first, modern electricity system in itself is one of the greatest engineering achievements of humankind. This might actually be the only product that we use continuously. Today, probably even the fact that you are watching this seminar means that you are using electricity, but you are pretty much doing it 24/7. So the product needs to be very reliable. And trustworthy power grid plays a major role in it. Now, a few words about the company that I work in, Eesti Energia. So this is one of the largest companies in Estonia, and it's kind of like a natural monopoly in the field of electricity after the Soviet Union broke down. And currently we are active in the whole value chain of electricity industry, from mining to energy production, to energy trading, handling distribution system, and also client services, which is more and more important area these days, building new types of innovative electricity services to clients. But today specifically, we turn our attention to the power grid or the distribution system. So Elektrilevi, you have probably heard the name. Elektrilevi is the subsidiary of Eesti Energia that manages the power grid and makes sure that the electricity reaches to customers. So here's some selected numbers from Elektrilevi. We have more than 650,000 smart meters. All Estonia is covered 100% with smart meters, making it actually pretty much the only company in Europe. I don't know about the world, but this is pretty important stuff of building innovative solutions on top of this. Then there are 24,000 substations and 37,000 kilometers of electricity lines, which is nearly a distance around the world. So just imagine that all of this needs to be maintained. Dealing with power grid failures is as old as the power grid itself. And the legacy approach or the traditional approach goes as follows. You receive a failure signal. You either receive it automatically from the system or somebody calls you. A team will be sent out to solve it. And two things can happen. Either the failure will be solved or the team will order additional resources to solve the fault. So the second is not so preferable outcome because then there is a double expense of solving the failure. But it happens because we don't know what is going on there and what do we need to solve. Now the bottlenecks of this legacy approach. First, it's reactive by its nature. So the process starts when the failure has already taken place. So anyway, the customer will get some bad experience. And the second point is that the solving the failure is 1/3 more expensive than the maintenance of the same system. So if we were able to kind of go there before the problem happened and maintain the system, then it's kind of 30% of monetary saving. Now, our idea, the initial idea of how to do predictive maintenance of the power grid was as follows. We wanted to use historical maintenance reports to predict grid failures. So each time when a grid failure has happened and the team was sent in place, then the team made a little report of what they saw and what did they solve. And those grid devices, it's around 700,000, are continuously sending various alarms and events. So on top of the consumption data, that how much to consume electricity, we actually receive alarms and events if something needs to be, if something seems to be a bit shady going on there. So we have this alarms and events data time series, and we have the legacy process has generated a large amount of maintenance reports. So it's fault detection plus what was done to solve the fault. And the idea was to merge the alarms and events that happened before the failure with maintenance reports, and we'll have the labeled dataset for training. Let's look at the data that we had, like just to get a bit better picture of what we are dealing with. So the alarms and events from grid devices looks a little bit like this. So the top right corner or top right area, you see that there is the ID of the device that is sending this alarm. And then there is a type code. There is more than 200 of those type codes. So 200 different kind of alarms and events can be sent by the devices. And then there is the sample maintenance report. Of course, it's a bit larger, but the most important part is the description of what was seen and what was going on. So for example, here we see that, and this is really example, that customer circuit breakers, C-phase bad, contact fixed, checked and problem gone. And the second example, one old and rusty shield, this house is collapsing. And you see we probably already see the problem here, but let me just point it out. So it's a free text. Specialists who go to the place of maintaining the failure or solving the failure have their own style of filling it. And different terms have been used to describe the same fault as well. So there is like all kind of variability going on there, how these reports have been like actually put together. And actually the result was that maintenance reports are too low quality to be used as a source of annotations. And it wasn't just the case that we weren't able to kind of manually, we would have been able to maybe taken the reports and manually label them, but still we didn't know whether the information there was even correct or not. So, but for us, this was also an interesting discovery. This was something I would call a serendipity moment or a lucky discovery, actually. Because the failure to use this maintenance data for labeling showed us the need to refine the process. So the need to refine this process of specialists going on place and then writing something down of what they did and what was going on. Also, the data governance will get additional task to make sure that the data that is being gathered corresponds to foreseeable future needs. So in Eesti Energia, we have data management, data governance processes in place. There is like specific person responsible for data sets, but it's more like a formal thing going on. And so far, it hasn't been so much into thinking what the business might need, what the data needs to look like if the manager wants to do predictive maintenance in 2 years. And also, very importantly, this knowledge that we learned from this one failure can be expanded to all processes across the organization. Now, our second idea of how to approach this was as follows. So recall that we had these 700,000 devices that are continuously sending raw alarm events and more than 200 different types of alarms. And why I say raw is that there is nothing being done with it. It comes as devices sent them, and sometimes we don't know why devices sent them out. And our plan was that, okay, this is actually somewhat annotated data set already. This is not like your consumption data because something shady is happening there. So we have some kind of annotations. So our plan was to give this data, this raw data to specialists to label problems manually. So they look at this time series of alarms and say that, okay, this is not normal. These alarms are like too frequent. And when I look at the type of alarms, then I think that something is going on with the voltage, for example, or some phases or something like this. And then our plan was to send out the field crew to validate the labels. So our specialist would label some few hundred cases and then we send out field crew to validate. We did 200 examples like this. And the results were as follows. The fault was detected only on 56% of cases, and it's not good enough for predictive maintenance. It's actually more expensive to do it this way than just sending out field crew every time then the failure actually happens. So this approach didn't work either. What did we learn? Maintenance reports are not good enough for labeling. This was the first thing, and we need to fix it. We need to refine our processes and to refine also the data governance process. And we can't label manually based on raw alarms and events, just too messy. And even specialists couldn't find like kind of the reasons there. And solution is to refine maintenance reporting, build ML predictor with alarms, events as features, and knowledge from better reports as labels. So we are building now up this data set of refined maintenance reports. This will give us like better labels and the time series of alarms and events. There we can produce some features out from them. And we have already tested the accuracy is growing with every day as the more data is coming in. But a little bit for inspiration as well. Eesti Energia might seem like a big old company and not very interesting one, but electricity industry itself is going through a very disruptive processes right now in the next 10 years. And the following things will happen. We know, we can pretty much see into the future. First, there is a rapid growth of renewable energy, which means that the energy production will get unstable. Right now, we are like shoveling the coal into the ovens. This is a very simple thing, and we can control how much is produced. But when the renewable sources come in, then they will only produce electricity when the sun is shining or the wind is blowing. And but there is like this one interesting thing which might not be immediately clear, that inside this electricity system, the consumption and production needs to be balanced at all times. There couldn't be actually a situation when somebody is like producing more or consuming more than the other side is doing. So we need to balance this system all the time. Very tricky. Then the second large thing that will happen is that connected devices, storage, photovoltaics that are installed inside people's homes enable to start orchestrating the energy flows from distance. So pretty much the IoT. And the third thing, electric vehicles will create a new type of energy consumption, which we haven't seen ever. Grid has not built with that in mind. And one electric vehicle can actually take more electricity while it is charging than the whole household. So this is what is going on, and all of this system needs to be balanced. And so the new energy system that we need to build will be built with technology that enables to first predict, control, secure, optimize, and trade energy in real time, 24/7. And as you see from here, this is actually pretty much like how much the machine learning and data science can put into energy, modern energy system, to build it up to even enable such an environment. And that was my last slide. Thank you. You can get inspiration for your new startup as well from Enefit IT. I recently wrote an article where I summarized 13 IT-based business opportunities in energy sector. So check it out, maybe something interesting, and you'll find me at this from this email address.
Thank you. As a reminder, if you have any questions to Kristjan, please write them in the chat and I can read them out. I really like your kind of how you talked about kind of that you have these case reports and then you get some codes and then you try to detect like when the failures happen and kind of prevent them. This, like I'm from like a biology background, so this sounds like personalized medicine to me. Mm-hmm. So you've got kind of doctors' reports that they are written not for the machine learning in mind. They're written to document things and maybe manually go back. They sometimes add some codes to that, and sometimes there's some like other measurements coming from different systems, and then you've got this huge system of health data, and then you try to do the same thing. And I think it's like your challenges are not unique in a sense that I think that many of the challenges are almost exactly the same in kind of health data, trying to use this in the same kind of predictive modeling to prevent, like, for example, to prevent health events.
Yeah, and I think that the same problems probably expand to every environment where lots of devices are sending like some kind of data, and we want to do some kind of predictions on top of it.
But how do you, like, one question from me, and then I move to the questions from the chat, is how do you balance in health data, they talk a lot about that doctors don't have time to fill in data in a format that would be useful for machine learning. Mm. So how do you balance that like these repair crews do not want to kind of have like checkboxes with like 200 different alternatives to kind of report faults so that you could build better models? So how do you kind of balance the need for well annotated data with kind of what's operationally feasible with like repair crews? Mm. Or is it an issue for you at all?
Well, right now it is an issue, and we still hope to push those maintenance crews to the filling out it in some sort of structural way.
Yeah, so I think like this is kind of, these are open issues for in many fields. So the questions now is how far is the state of the art from Eesti Energia being able to identify 80% of the devices operating in home from smart meter external readings via machine learning?
Yes, I know what the question is about. It's probably about like this non-intrusive load monitoring, which aims to kind of take your consumption data and then detect what kind of devices you have inside the home. The problem right now is that, as you might know, we have hourly meter data in Estonia available. So we have 1 data point per hour. As I mentioned, it's 650,000 devices sending data. And even this 1 data point per hour is a pretty a lot. But in order to do this non-intrusive load monitoring, we need like data with frequency of, let's say, 5 minutes, or better still 1 minute. And this is currently not happening. We are discussing this a lot, but I can't give any kind of...
What's the challenge in kind of increasing the frequency? Is it storing the data or transferring it? Or...
Yeah, it's all around those things. It's well, the storage we can solve. It's pretty much just putting like more money, but where is the business case is one question, right? Yeah. If you need to store so much more data, but also to transfer this data from those remote devices. This is not so easy actually, because those devices, their main job is still to measure your electricity flows, and this communication, well, they are not so strong there. And sometimes, I don't know, like communication is bad, and we have problems of getting the data and so on and so forth.
Thanks. What are you planning to change in order to cope with increasing amount of electric vehicles? Is it an issue for you at all?
In Estonia, electricity grid, power grid is actually very strong when compared to other countries in around Europe. And for us, as the electric vehicles, they will come like step by step. They won't come all together, like, and we can handle this, but it most likely it produces like interesting opportunities of starting to do some kind of the concept is flexibility, of trying to do some flexible energy management, such that we orchestrate of what devices and how or what electric vehicles will charge at any point given time, and we compensate to the drivers if they can charge for this specific time. This could be an alternative of like investing into building a larger grid, for example.
I think are we out of time? Okay. So there was a question about like what kind of improvements they made regarding using machine learning to analyze failure descriptions. But I guess it seems that your main new thing is actually you're actually starting to collect the data to be able to use machine learning. But have you already been able to see that you can, now that you have better labels, you can kind of use machine learning? Yeah,
we can use, but the accuracy is still too low to kind of use it in production. And we see that as the data is coming in, that we are able to make it better.
There's a question about how increasing renewable energy will affect energy production. You kind of covered that.
Yeah, right? It affects a lot because, as I mentioned, the main aspect there is that it's unstable, so it pretty much means that you guys looking this seminar have a lot of work to do. In this sense that we need smart algorithms that will decide how to take this electricity that is being generated when the wind is blowing, and to store it somewhere, or to manage the whole system like this, that at each given point of time, our production and consumption are always like the same.
Okay, thank you. I think that's it from the questions. Thank you, Kristjan. The next speaker is Rao Pärnpuu from Starship, talking about self-driving robots.
Thank you. Hi, so my name is Rao. I'm from Starship, and today I'm going to be talking about how to use, or how do we use datasets to develop and operate self-driving robots. So what is Starship, and who am I? Starship is a company developing sidewalk self-driving autonomous robots. So the idea is to model this after a pedestrian, doing the things that a pedestrian does, and to sort of cover short trips to to help out with last mile logistics. So doing any kind of deliveries that can be done in a couple of mile radius. It can be food, it can be groceries, it can be whatever else that's a physical good that needs moving over short distances. And we operate across the globe in several different locations. We do grocery delivery, we do restaurant food, hot food delivery, and we have our own app for that as well. So I work on the autonomous driving side. I'm responsible and leading our efforts around data sets and all of our sort of performance monitoring, performance tracking systems. And also I'm the product manager responsible for our self-driving stack. So I'll be talking from these angles a little bit today. So the core thesis that I'm going for today, that I'm sort of want to prove or will try to prove, is that datasets are at the heart of developing and continuously operating self-driving robots. This continuously operating is something I want to emphasize a couple of times during this presentation, because when most people think about self-driving cars, self-driving robots, then you think about, okay, how do you build these systems that can actually make these smart decisions and operate autonomously? But as important of this is the other side of the coin, which is once you actually have a working system and you deploy that, you need to be working a lot on making sure that you can still continuously operate and continue to be driving at a performance level that you were sort of aiming for. So where do we use datasets at Starship? I'll do a follow-up with a practical example later on. So I'll go through these points in a little bit more detail, but here's a general overview. So you start out by setting product development priorities. So deciding like, what are the things that you actually need to develop? What are the things that you should be prioritizing to work on? Defining the problem space you're trying to solve. So data is the specification in several different ways. The way you build up your data set is going to define the scope of what you're trying to solve, whether you're using machine learning models or any other types of approaches. Then you have this classical part, development of algorithms. So you use data as input to train your models. You use data as input to build other software systems. Testing new systems, next logical step from that. Also simulations. You can use data sets to calculate key performance metrics. So you can build specific data sets to understand how well your system is performing. And as I mentioned as well, you use data sets to track your performance in the real world. So we'll dive into these a bit later as well, deeper. So one sort of very critical or important aspect around building self-driving robots, whether it's cars, sidewalk robots, or something else, is your sort of operational maturity influences quite a bit what your approach is and what are the sort of focus points that you have to take. You start a new company, you start out with the first prototype, then you start at level 1. So you have this physical supervision. For our robot, that meant the person walking with the robot being able to sort of control it when necessary. For a self-driving car company, that might mean a safety driver in the car ready to take over or actively driving. So you start at this level, and at this level you sort of have some risks reduced because you have a person always in control of the system, which means that you can more focus on actually starting to develop your first systems and developing your first algorithms. Then after you have something that sort of works well, and you can start trusting the system more and more, you can actually move over to active remote supervision. So this means you might not have a person physically with the object, but there's going to be somewhere remotely keeping like an active view of what the robot is doing and directly controlling it when necessary. That's a level you can operate at some time as well. And then the third level that you're sort of eventually are aiming to get to is this passive remote supervision, right? That's where you start getting these huge gains in autonomy. In level 1 and level 2, you have like persons actively involved in the driving, so you're not actually getting those efficiency gains, but it's that third level where you start getting those efficiency gains. So you have this passive remote supervision where you're not necessarily actively involved in every second of every robot doing something, but you're doing this overall supervision. So fleet tracking, health monitoring, etc., everything around that. So where are we with Starship currently? We're pretty strongly on that third level of operations. So vast majority of driving is covered by passive remote monitoring and done without that type of direct supervision. So just as an example, this year we've been covering over 1 million kilometers. That's equivalent to a trip around the world every couple of days. And in 1 year of operations, as I mentioned, we're sort of driving at pedestrian speeds. We're modeling ourselves based on pedestrian. So in 1 year of operations, we cover a distance equal to what a pedestrian walks on average in several dozen lifetimes, so several thousand years. So that's quite a bit of experience to get in a single year. We do lots of different things, driving on the sidewalk, also road crossings. So we're doing right now tens of thousands of road crossings every single day. So trying to get across car roads. And the vast majority of them are done without this type of direct supervision. And as a consequence, we see millions of vehicles, millions of pedestrians every year that we sort of have to correctly identify and then behave around autonomously. So that's the context of where we're trying to solve these problems and sort of what are the focus points that we have to have. So why are data sets important for making all of this work? To try to condense that down to a single sentence, I would say it as something like this. For successfully concentrating a vast and complex environment into a technically solvable and humanly understandable problem domain. So quite a mouthful, but let's break it down a bit. So you have a large world. As I mentioned, we cover an entire lifetime's worth of experience with a 1 week of driving. That's a lot. That's several dozen different areas all across the world. That's a lot of miles. That's a lot of interactions. That's a lot of everything, pretty much. So you have to concentrate that down somehow to actually work on it as a solvable problem or a solvable development sort of focus. So you use data sets for that. You build the data sets based on that environment, but you can condense down that sort of information size, trying to not lose any information complexity. And by doing that, you make it technical solvable in the sense that you can actually then use that data set as a proxy of that environment to develop your algorithms, train your machine learning models, or whatever else decision making you have to do around building these kinds of systems. And the added benefit that you get from that is that you're making the problem domain more humanly understandable as well. So as an engineer, as a product person, as a data person, whoever has to work on this system, they have a better understanding of what are the types of situations we're solving and what are the types of situations that we're dealing with. Okay, so let's go into a hypothetical example. You go through these points and see how would we be potentially building these data sets around this. So I'll take an example from the same space. Pretty straightforward thing to build. Identify the location and state of a traffic light at a crossing. That's one of the core things you have to solve, whether you're building a car or a sidewalk robot, and that's something you have to do well. So let's work through how we could be building data sets, different types of data sets for such a project based on the areas we discussed before. So these 7 points that I went through before. Let's go one by one. So product development priority. You start by trying to understand whether this is a system you have to build right now. Do you need that? So for that, you might have like a data set of help request logs from the robot. So every time the robot needs, let's say, active remote operating or active remote supervision, it can file a help request, and you have all this information. You can go through this and build a data set from that. You can categorize the system situations, label them, identify which of these are traffic light crossings, and as a consequence, you might see like, oh, we're spending a lot of time on these traffic light crossings where we need help. We should build something to make this better. So that's going to be like a good win for the company. Next step you go from there is, okay, we know this is the problem we need to solve. So what's the problem space? How do we define that? When you decide to build a system to identify traffic lights, you're not going to do it for every traffic light in every single country in the world. That might not be what you need. There might be specific business cases. There might be specific strategical requirements for this. But you have to somehow scope out the problem domain and specify through data what the problem is you're solving. So this data set might be a collection of like crossings on a map. Like these are the types of crossings we need to solve. These are the types of crossings we need to handle. It might be a collection of time slices of video situations where you've seen like, okay, this specific crossing here, there's 10-minute time slice. You have a traffic light here. This is the type of situation we need to solve. And there's like 10,000 of these. So these are the 10,000 we need to handle. Whatever else, which way you want to build this. And what goes into this set will basically define the problem scope for the engineer. So that's where the engineer knows that, okay, this is the problem I'm solving. Not this general vague concept of identify traffic lights, but the specific problem space of these cases need to be solved. So then we get to this classical part, which is usually talked about the most, which is algorithm development. So let's say you're using a neural net to sort of accomplish this task. So you build a data set of images with bounding box annotations, for example, for traffic lights, along with labeling those images for whatever else information you need. So you might draw bounding boxes here as an example around traffic lights so that you can train object detection systems, and you can do some extra labeling here as well. So you're probably interested in saying whether it's a red light or a green light, whether it's blinking or not, or whatever else that might be of interest to you. Then you move on to testing, right? So testing set can be a subset of the data you prepare for development. So you can actually test your system, see what the performance is. And this is usually something that's going to be like a continuously growing body of annotations as well. So you might build a system, you might get more driving experience, you're going to see new samples, new edge cases, you might go into new business directions. So this sort of testing set is always continuously expanding, getting more comprehensive. And that's the sort of data set you use to actually understand how well your system generalizes and where is it working well and where it isn't. So you use this to evaluate system performance. You might also do simulations. So you might build some data sets with either partial or fully synthetic data. And the aim of this would usually be to diversify already existing data. Going with this traffic light example, this might be that you're playing with lighting conditions on the image, playing with different camera exposures, like if the image is overexposed, you still see the traffic light. You might play with partial visibility on the traffic light, so you cover it up halfway through and see if you can still identify it correctly, or whether you can identify whether it's covered up or not, and so on. So you can create more data to actually train better systems. You might have data sets for calculating KPIs. So a lot of this can be done based on the same data sets you used for development and testing, but you might have some specific metrics that you want to answer where you actually need to make custom purpose-built data sets that actually help you answer, like, what's the performance in this specific situation comparing these two parameters. And this can also include scenario testing to estimate system maturity. So not just testing traffic light detection, but testing a more comprehensive scenario to actually work on this. And the last step then is this continuous performance tracking. So you build something, you put it live, it's working in the real world, you have to understand whether it's actually working as well as you sort of tested it on and built it on and went through all these steps, and you sort of continuously have to make sure that it's still working the way it's supposed to. So you might build data sets from fresh operational data to estimate like current system performance. You might look at data from the last hour, the last day, the last week, whatever time scale makes sense to you. And you might either use that data somehow automatically label that, or use manual labeling to sort of get that input depending on your needs. That's usually a more simplified labeling structure to facilitate this getting a comprehensive overview quickly. So here the aim is to have large enough quantities in a very short period of time. So your aim is to simplify this structure and get as much good data to understand what's going on. And this can also be then input to the other data sets. So the main point here is that, if you're building these types of systems, then data sets are really present across the entire product development lifecycle. It's not only there for developing your algorithm or training your neural net, but it's already there several steps before when you're making your product development decisions, and it's going to be several steps after that, even once you've deployed a fully mature system, because you still have to make sure that it's always working up to the performance parameters that you have. So it's going to be loads of different data sets across the entire life cycle through building, testing, deploying, and then performance tracking, and going through all the iterations round and round and round. So the world is complex and it's always changing. We don't have full environmental control of where we're operating in. The world has a mind of its own. It does its own thing. It changes in several different ways. It's not always going to be static. So you need to rebuild that world as a sort of concentrated and effective collection of data sets to actually develop something. But then you also have to be continuously tracking, rebuilding, expanding those data sets to make sure that you sort of have this functional equivalence between what your data looks like that you're actually using for all of these things and what the world actually looks like. That's not always a trivial problem to solve. So, the first thing you might go for is that, okay, but, we're doing this X hours of driving. Let's just look at the same X hours of driving and see what's going on there. And we have this perfect picture of everything that's happening and how well everything is working. Well, that sort of defeats the point, right? You're building an autonomous system that you're hoping does things by itself, and you're sort of expecting that to give you that cost reduction. So if you actually then review the entire full amount of data manually, then you sort of lose the entire business point of the system that you built. So you have to be a bit more smarter about it. A couple of learnings that we've gathered so far through building these types of data sets. So one is you have to be deliberate about what types of behaviors and scenarios you're targeting, right? There's a lot of stuff that happens in the world that actually isn't that interesting. Just let's bring a self-driving car example. If you're driving on the highway, 99% of the time, you're going to be in the same lane and just speeding up and slowing down based on what the car in front of you is doing. It's a very boring and event-free environment, let's say. So you don't have to maniacally go through all of that to understand that the system is working well. So you have to be specific about what types of behaviors and scenarios you're targeting. But you also have to leave space to discover things you didn't think about. So it can't always be that I know where the interesting stuff is happening and I go there, but you also have to have the space of admitting that, okay, I might not always know where the interesting stuff is happening, so I have to take this wider view as well. So you have to balance these two things. Automate as much of the data building as you can, and then focus on making sure your automation is working as it's supposed to. That's sort of a scale effect that you're going to have, right? There are certain types of data annotations or data labeling stuff that you can do that sort of don't need human input or needs very little human input to actually get quality data. If you can build those systems well, and you sort of focus on making sure that those systems work to the performance standards they're supposed to, then that gives you a scaling effect that can be very useful. And following a similar way, like starting with simple pieces of information that you can sort of reliably extract or then efficiently annotate at scale if you're using like manual labeling, and then combine these pieces into richer and more complicated data sets. So that follows a similar principle. You want to simplify the process as much as possible to get those scaling effects, but you can always use these pieces to go into more richer and complicated environments. Overall, a healthy amount of paranoia is good here when you're doing this sort of stuff. You should always be thinking about what is it you don't know that you don't know, and how can you sort of figure it out. So that's a good sort of approach to take when working on these types of problems. And we're still learning every day, figuring out the best ways how to sort of efficiently build these systems and sort of meaningfully build these types of data sets that we need to use for different aspects of the business as we scale into more and more driving. Yeah, and that's about it from my side. So thank you. You can visit our webpage to find out more about the company, and also if anyone wants to write to me, then my email is there.
Thank you for the excellent presentation. We can now move to questions. Reminder again, if you have any questions to Rao, please write into the chat and I will read them out. So there is the first question is, what tools are you using to organize and manage your data sets?
Lots of different stuff. I guess one of the problems is that you don't really have a very mature software ecosystem to handle these types of problems. Some of the things you have to build yourself, some of the things you're sort of hand-picking and hacking together. So a couple of examples, like for storing this type of data, or especially like manual annotated or labeled data, whether it's manual or automatic, we usually use like S3 or MongoDB to sort of store and access that information. And then, yeah, we have some custom purpose-built tools to actually manage those information flows and put that data together, or we might use some open source annotation tools as well. So it's a mix and match of stuff, not really a single ecosystem.
Okay, so how, going forward with this, like how much of your effort is actually kind of building tools to be able to annotate data sets, or like?
Well, I'm that specifically less. So, okay. So this sort of annotation part, we've been consciously focusing on this less, because then that's like an engineering resource you're spending on tools instead of the core technology that you're supposed to be handling. So for like annotation, we've used some open source tools that have been fairly good. CVAT is something I would recommend. That's really good, has all the basic functionalities. We also use for several different types of data, like outsourcing partners that have like all their systems and tools purpose-built, and they have had their engineering focus in building the best tools possible, along with maybe like a labeling, like human labeling for us as well. So we've used quite a bit of like different services as well.
So are they kind of like services that they actually label the data for you?
Yeah, both. I personally, like, this is a preference question as well, and a problem domain person. I personally like full service ecosystems, because that offloads quite a bit from me. Like I just have to make sure that the quality we get is as good as we need. But I can sort of offload this idea of managing this workforce and everything else. So that's frees up your time to work on the other more complicated problems.
Okay. So now a few questions from here. Did COVID-19 affect your vehicle performance somehow and made you to create new data sets?
Yes and no. For the time being, the world got a lot quieter, so that made stuff simple. But that did have a noticeable performance effect. Like, for example, if I remember correctly, in Tallinn, for example, the traffic density died down almost 50% during like April. Okay. And I guess it was a similar thing in other countries as well, in the US, where we do most of our operations. So that makes your life easier, right? So you have less cars to worry about, you can be faster and so on. So it definitely affects performance as well. Yeah.
Okay. So you mentioned this kind of being paranoid, healthy paranoia. And I mean, I completely agree with the principle. I'm thinking about how do you build a machine learning event detection system that's paranoid?
Oh, that's a good question. Well, there isn't a single simple answer there, I guess. I guess the answer there is that whatever you build, you shouldn't implicitly always trust it, right? You sort of build up that confidence that the system works in several different types of scenarios, and it can work at a mature level by you know testing on large data sets and data sets with large variety. But you should always go back at some point in time, like not constantly every day maybe, but at some points you should always go back in time and make sure that the sort of assumptions you made are still correct. And you know, there's some things you can do, like, well, let's say more automatically there, like you can do some analytics based on the dataset drift, right? You can like compare the dataset that you trained on to the dataset that you're collecting now today from the environment you're driving in. So you can do some dataset drift analysis there. And there are some other techniques that you can use, but at the end of the day, you sort of have to go back and recheck, not always, but occasionally, to make sure that everything's sort of working. Take like an agnostic view that I'm going to assume that I don't know anything, and I'm going to sort of rework myself up to that knowledge, and then you usually find some surprising information.
Okay, but like if you can go into a bit more like specifics, like I mean, like if you can imagine that like if you have this recording of like driving history, I mean you don't have too many frames per second probably, but still I think it's most of the time nothing happens.
Yeah, exactly. Like the vast majority is just like
so how do you
empty sidewalks and you're just driving straight.
So yeah, so what are kind of some of the things that you would at least kind of use to kind of discover that there's something happening now, and therefore we should kind of at least try to kind of learn from these situations?
Well, that you can do based on the sensor data that you get, right?
Okay.
So that's a lot of things. So we have quite a big variety of different sensor sheets on the robot, so you can use that as well. Like a very good trick to actually understand the relative performance of stuff is that when you're building these types of self-driving systems, you don't want to build them in a way where you have a single point of failure, right? For almost every important task that you're doing, you want to have at least two systems trying to do that, preferably even more. So when one of them fails in a specific case, there's always the other one that's actually going to make the correct decision. So that's, I think, one critical actually information point that you're going to start getting, where you can actually see like these types of problems popping up. When like one system made this decision, the other one made this one, they don't match. Like, okay, why is that? Is one not working the way it's supposed to, or is there something else going on? And that's, for example, a useful.
Yeah, I think that's conceptually very simple, but also going to be very useful. Is that like if you have two systems, they don't have to be perfect for them to.
Yeah, exactly.
And if they disagree, then you know that you can kind of improve.
Yeah. For example, going back to this like hypothetical example of a traffic light, right? You can have a couple of different things there. Yeah, you're going to train a neural network to identify traffic light, but you also might manually map them, right? You can create a manual map of them, and so whenever you have a discrepancy between the map and the live like neural network detection, you know that something's going on. Right? There's a like discrepancy here that you have to investigate. Then you can use those data points to sort of understand like what the overall performance is and how it's drifting over a certain period of time as well.
So you also mentioned this like that you like full service companies, like but obviously you're trying to build these self-driving robots. So you can't kind of outsource self-driving.
No. You can't outsource product development decisions. You can't outsource technologies. But what you can outsource is maybe quality control and project management. That's the side.
Okay, like if somebody's kind of collecting manual annotations, you can kind of
and also the tools that you use.
Okay, okay.
You don't want to become the company that's building the best tools. You want to use the company that's building the best tools.
Okay. The one final question here is that usually data quality is a problem in machine learning, and so how big problem it is in self-driving vehicles?
Well, it's a difficult question because it depends a bit on what you mean by
data.
what do you mean by data quality, right? So in some sense, out of necessity, you have to make sure that the data is at good enough quality, depending on how critical of a system you're building, right? But it is a headache. Like that's a constant headache I'm dealing with. I think that's the #1 frustration that I have. If anyone talks to me about data and data sets, and like sooner or later, I'm gonna go off on data quality. But so it matters a lot, and it's like this constant annoying thing that you have to constantly work on. It's work that you don't really always enjoy, but actually makes big meaningful differences. Yeah.
Okay. So maybe one final question.
Yeah. Go ahead.
So this like going back to data quality, like how I mean you could like one way I could think about like different types of qualities. Like you could think about quality as image resolution, but like what you get from the camera, and like quality in terms of event annotations.
Yeah.
Like how often do you feel that that you really want to have like better sensors, and how often you feel that our sensors are fine, but we're just not detecting things like that. The signals are clearly in the sensors. We're just not able to learn them that well.
Well, I guess it's both. I guess. I mean, you always want to have better stuff, right?
Yeah.
If you had free reign, you could build $1 million robot, then you would be like you could be a happy person. But so there's always going to be constraints there. I think most of the problems are still like let's say data quality problems of the second side, right? You actually have the underlying signal. You just have to be smarter in how you're using it, how you're solving it, and what are the technical solutions that you're using. I would say 80% goes under that sort of direction. And then occasionally, when you have exhausted all of your software sort of approaches, and you still are not getting to the place you're getting to, which is rare, but it does occasionally happen, then you understand that, okay, maybe we should go back to the drawing board, and maybe we should add something to the robot. We're continuously adding sensors as well. I think we add a few things every year, or replace with better versions every year. So that's a continuous process in the background as well.
Okay. Yeah. Thanks a lot. Now we're moving to the final presentation for the day. Taivo Pungas is going to talk about Datasets, the source code of software 2.0. Floor is yours.
Thank you. My name is Taivo, and I will talk today about this concept. I will explain it in a minute what that is. But first, let me introduce myself. So up until very recently, I worked at RIF as a startup. I built up the AI team there from nothing to about 20 people, and a very significant impact in production and to the business. And I've previously worked at different Estonian startups in various data and AI related roles. Today, what I'm doing is I'm focusing on building software and building solutions for quickly assembling good data sets. And this presentation is kind of a small peek into what I believe the good patterns are. So when I say data is the source code, some of you may have heard about it, and I will explain that in the next slide. This slide shows the data set which I will use to illustrate my ideas. I didn't want to make it like a fully theoretical presentation. I want to give you actual examples of what I mean, because this is the most powerful way of conveying the ideas. The data is basically randomly sampled images from a classified ads website. So people are posting or uploading images of things they are selling. So if you look at let's say on the top part of this slide, there's this like software 1.0 concept. You have source code, C++ in this case. You have a compiler, you have a compilation step. It turns into a binary, and you can take that binary and run it in almost any platform you want. And the clear analogy and the software 2.0 way of thinking. This concept, by the way, was I think introduced by Tesla's director of AI, one of the well-known people in computer vision, Andrej Karpathy. So instead of the source code, you have the dataset consisting of a bunch of labeled examples. Each example is a pair of input-output. So in the case of image classification, the input is an image, the output is a class, or if it's a binary classification, then it's yes, no, or one of two options. The training step or the compilation step of software 2.0 is taking the data, running it through the neural network, optimizing the weights, and the model, the output of this compilation step is a binary, in this case, weights, perhaps with some metadata or additional information about what structure to load those weights into. And this, again, you can run on almost any platform as an independent module or independent program. So this is the concept of software 2.0. And one thing I think is interesting about this is if you took this, like your first thought about how the source code of software 1.0 applies to the software 2.0 world, could be that maybe this source code, like the equivalent would be the training code, because you have some Python code doing the pre-processing, the model training, etc. But in reality, that's not true. Because in most cases, in most applications, unless you're on like cutting edge research, the major impact or the biggest impact you can have on the performance of your system will come from improving the data set as opposed to improving the model training code. And I would go so far as to say that if you're if you're building a practical application where you're doing something relatively standard, I think image classification is a perfect example. If you every week you consider what should I focus on this week to improve, that would improve the performance of the system the most. For the first 20 weeks or the first 20 iterations, it would be working on improving the data set and keeping some extremely standard model architecture. So in this world, there are first signs or first implementations of dataset compilers. The simplest way, or I would say something that's very standard and I think relatively often used actually, is you take some pre-trained model from Keras applications, you fine-tune it on your own data, and this is a relatively straightforward way of compiling a dataset into a model. Uber has this library or project called Ludwig, which where you declare the input and output types of your input data type, output data type, and data source, and kind of that's it, or that's the most you have to do. You have more configuration options, but it's kind of the first, I think, sign or step towards these no-brainer compilers. I haven't used it myself though. And there are tens, if not hundreds, of companies, and many companies for whom this is a feature, this machine learning as a service, where you have the premise is come with your own data set and we will take care of everything else. So if you bring the data set, they will turn it into a model, they will deploy it onto some servers, they will give you an API to predict, etc. So there are many, many solutions like that out there. If you take this view, if you live in the world that I just described, you will start seeing that many things are wrong today, or you will start seeing many things that kind of disturb you. So in my experience working at AI teams and also recently consulting or advising some startup AI teams, I've started to see some anti-patterns. And I think the generator of all those is the belief that the data set is kind of an annoying detail that you have to get over so you can get to the model training, which is the exact opposite of what I just explained. So this is completely wrong, I think. And this generates several like specific instances of this failure. So if you think about the goal of a product or goal of a prediction system, it is completely defined by two things. One, the dataset which you evaluate this on, like this model or this predictive system on, and two, the scoring function that you use. So it is super typical for companies to leave this into the hands of data scientists or engineers. Like, you know, just to, I don't know, label the data somehow, pick a function to measure the performance, and that's kind of how they get the results. And this is a really bad pattern, because that means you forfeit all of the control over the system to someone whose job is not really to figure out what the system should do. So product managers, project managers, potentially up to like executives should be the people defining what the purpose of the goal or purpose of the system is, as opposed to, you know, like someone who happened to spend some time, a couple of hours on learning the dataset, or you might, that's one of the dataset part. And in the scoring function part, like you really want to think through what you optimize for, not just take the first one that like was auto-completed for you from sklearn. Another bad pattern is, and this is something I briefly mentioned already, focusing on the model, not the dataset. I think, again, in this world, it seems so stupid, and it becomes very clear if you think about the analogy. Like when building software 1.0, how much time do you spend thinking about the compiler? Like most of the time, you don't even want to spend any time on it. Sometimes maybe you need to like tinker with some flags to make it like to improve the like optimization or change the optimization, use the debugging options or whatever. But most of the time, you just want it to work, and you don't want to spend time on it. You want to spend time with the source code. And same with software 2.0. It's an interesting, I think it's even a paradox. I think the reason this is, or why data scientists often prefer to focus on models, is they signed up for the field. The reason they got into the field was to work with models. They didn't get into the field to go through like tens of thousands of images. And this is my explanation for my observation that most data scientists hate working with data sets. It's weird, but like I said, it's a paradox. By the way, the best ones kind of spend most of their time doing it, and I guess have learned to love it. And another pattern, which is kind of okay, is outsourcing labeling. So if you do, let's say, a binary classification task where out of the data set I showed you before, you want to detect whether the image is of a coin or not. So all of the examples I'm showing here are kind of trivial. Like the answer is obviously yes. Or maybe if you wanted to do a segmentation or segment out the coin here, it would also be really trivial to do those. And outsourcing trivial labels, like nothing can go wrong because almost any person in the world can understand exactly what the policy is. The bad part, or the anti-pattern, is outsourcing judgment calls. So I found this, like I didn't really have to spend a lot of time searching for this. They kind of naturally came out of the dataset. The leftmost one, it is a coin, I think, but it is somehow on some sort of loop. Maybe it's an earring, maybe it's some decoration, but it's like, it's an edge case. Same here. It looks like a coin. It's probably not a coin, but it looks similar to the leftmost one. This one, it's a pile of coins. And like, is it a coin? Well, it's really difficult to answer that question. And the correct answer is, it is not a question. Like you shouldn't start like metaphysical discussions about what is a coin. You should just think, okay, what's my business goal? Should I consider this like yes label or no label? And this should give you a relatively simple answer. What happens if you outsource this is some random person somewhere makes your like core business decisions, and this is really not what you want. And the rightmost one here is like, it also looks like a coin, but it's in a box. So maybe it's a commemorative coin, maybe it's actually a prize, maybe it's not the real coin that at some point had cash value. Again, all of these edge cases. So now I've talked about the anti-patterns. The core pattern, or if you remember one thing from this whole talk, this is the one thing to remember. This is the generator of all the good patterns. Immerse yourself in the data set. You as a data scientist, you as a product manager, you as a project manager, if you're at all related to the prediction system that is being built, get really deep into the data set. And it's really straightforward to do that. You have to look at examples. That's step one. Then you have to look at more examples, look at some more examples, and finally look at examples. It might get tedious at some point, but let me go through these slides again and show you a couple of things which you should figure out or you want to notice when you're building any prediction model on top of this data set. So first slide, we can already see that there are these two images here, and it's like, I don't know, 10% of the whole data set, if this is a representative, which don't have a background. So they're either studio photos or the background has been somehow segmented and cropped out. And this is already interesting because maybe it is relevant to what you want to do. Second, in the previous and this slide, you notice that there's like two images of stamps, and I think on the previous slide there was also at least one. So it's quite common. It's quite a common class, or it's quite a common subject in these images. In this image, you see that some images have like annotations on top of them, or someone has put like machine-generated text on top of the photo. And in the last one, you figure out that, okay, some images are not actually natural photos at all. They are completely computer generated. It's either a screenshot or it's some sort of logo, but in any case, you need to be aware of this edge case when you're building something. To make it less boring, like if you keep randomly sampling examples when looking through them, it can kind of get annoying fast because you keep seeing the same like blend or generic mix of things. So what you might want to do is pick one example and look through a bunch of examples similar to that example. So if we take the book on the left and search for the most similar examples in this dataset, I will explain how in a second. Then you can see that there's a bunch of other books like that in the dataset, or a bunch of other books in the dataset. But also one interesting thing that you can see is there's a stamp which is stamp only, which is clear that it is a stamp only if you look very closely. And it might not even be possible to tell the difference between a book and a stamp, or a book and a postcard, or different kinds of things from these sorts of top-down flat views. So that tells you something about how hard it is to predict what you're trying to predict. The way this is, by the way, it's a real nearest neighbor search, or this is a real example. The way to build this, or I would say the trivial fastest way to build this, is to take one of these two libraries on the top, which give you fast nearest neighbor search through similarity hashing, and basically project each image into a vector space or into a feature space using either a pre-trained neural network or a network that you have trained yourself. Take activations from like some of the layers or one of the layers, and basically just assume that this is a good representation or a good vector of these objects. And for exploration purposes, that's good enough. Like it's I feel even slightly embarrassed saying this in an academic building, but this is like the engineer's approach to going through data. So a second example of the same thing, if you look through, if you find similar examples to the bus or toy bus on the left, you see there's like 10 toy buses we are seeing in the images on the right. One interesting thing that stands out to me immediately is there is this one example where there is a car or an image of a car on top of a box. I think it's a puzzle or some sort of game. And then it's an interesting example because it highlights that not all photos are necessarily taken of objects. It may be like the photo may be taken of an object which itself contains a depiction of some object, and you might not want to keep those. So if you want to, I don't know, find a nice toy bus to give as a gift to your grandchild or child, then like this would be a negative example, even though it looks like very much like a car. And the third example of looking through similar examples, when you look at this vase, I think, as a query, then so one thing that stands out for me is there are two images either of the same vase, like or very similar vases. This may be important to you. And the other thing, very similar or like on the same topic, there are two pictures like of the exact same object on the exact same background, but they're from like very slightly different viewpoints. So if you compare the two, like the corners of the two, how far the whatever the dark object on the top left is in both images, you can see that it's a different image. But these sorts of near duplicates may be something that you want to avoid or filter out or somehow deal with those. And it is important to know that these are there. Another common trick or common approach is to look through clusters of examples. So you can take the same embedding space and bring the dimensionality down with a common technique like tsni or UMAP. I usually default to UMAP recently. I think it's a bit faster with very high dimensional vectors. So on the bottom left, you can see the graph of like the 2 dimensions of the low dimensional representation, and each dot here is one image. You can explore clusters in this projection, and you can see that one cluster quite neatly corresponds to different kinds of stamps. You can also see that the other cluster corresponds to, like, I have no idea what. For the life of me, I cannot tell what the commonality between these pictures is. It may be, so this may also be, it doesn't have to be because of the embedding properties of the network or the feature generator. It may be because of the visualization method, but in any case, this is also like allows you to take a different directed exploration approach to going through the data set. Another approach, looking through high loss examples. So for the purposes of, again, like the engineer's approach in the binary classification task, you can just like sort things by loss being defined as the difference between the label and the probability that you predicted. So like I did exactly that. I found 2 interesting things. So one, this is a negative example. Again, this is a coin classification example. So this is a negative example. This is not an image containing coins, and this is an image containing coins. But this, especially if you squint, it looks a lot like coins. Like you have to look closely to make sure that they're not coins. And the 2 ones on the right. So this here, this is actually, it's not like super high probability predicted as a coin, but it is abnormally high. So it is one of the highest probability negative samples. And what this tells me, or what I infer from that, is the network based on which the network was, or what the model I used, it has a much stronger shape prior. It detects shape as a very significant feature because the color is different than most coins, but the shape is very similar. And the one on the very right is just the wrong label. Like I just labeled it wrong. And it's a very good way of finding mislabeled examples. Another approach is looking through uncertain predictions, uncertainty being defined here again. So if you have this, like most neural networks by default, or at least the standard ones, output the point estimate. So you get one probability, and it's not the real uncertainty, but you can say like the closer it is to 0.5, the more uncertain it is. And if you look through these sorts of predictions, you can find interesting examples. So there's a bunch of coins, they're all in a box. It looks like a collection. Maybe they're real, maybe they're not. But again, I definitely want to be the person who is labeling this. Like I want this to be labeled according to the best judgment of the product person I'm working with, as opposed to some random person looking through the examples and doing the labels. This one here, I think it's more straightforward in terms of policy or how some things should be labeled. But it's interesting because this is the clearest example I've seen in this data set where you can try it right now. Like cross your eyes a little bit, blur it out, and it looks a lot like a euro coin. Like it's extremely similar. And this is like really interesting finding for me at least. Second from right, again, coin in a box, maybe a real coin, maybe not. Depends on, like, not sure what we want to do with it. And the one on the right, like the rightmost image, it's some sort of ad or screenshot. I'm not sure why it was so uncertain, but again, it's good to know that we have these sorts of things in the dataset and we want to label them appropriately. Finally, everything I explained like previously, you can do yourself. It's relatively easy or relatively straightforward, but you always have to write code for that. It's not like you have good tools for doing so. So tools for doing what I just explained. For dataset exploration, which I kind of like, it's the category I'm talking about. The state of the art is download images, go through them in Windows Photo Viewer. Like this is literally what everyone does. I don't know of a better method that would, or like this is has the largest market penetration. There's one open source solution which I found. I haven't used it myself, but I explored it a little bit, which allows you to go through large data sets. I think it didn't seem very optimized for images, but it was like it had at least a minimal functionality, maybe like 10% of what I would want from this sort of tool. There's Aquarium, which is a Y Combinator startup, which is pretty expensive. It's a commercial tool, and they provide some of the functionality, and they allow you to explore the data set, and that's kind of their core focus. And there's a whole category of tools which I think they're not explicitly designed for that, but they allow you to explore the data set. So they're designed for like building an AI through only labeling, no code writing necessary, so no code AI. And in the process of doing so, you kind of interact with the model. You can see what sort of predictions, like whatever the model behind there is making, and you can explore more of the data set using these tools. Lobe is the only one that, as far as I know, the only one that has a free version. The other two are only paid. That's it. If you want to see more of this sort of my philosophy of coming from the background of data first or dataset first as opposed to training first, then follow me on Twitter. I'm most active there. Or if you have any cool tools you want to share with me, if you want to ask questions or just share comments, please feel free to email me at taivo@pungas.ee. Thank you.
Thank you. So there's one question here, which is if software 3.0 had to be a thing, could you envision some prospect for it? Is there already some signs you'd see that is leading to the next level? There's like example like meta learning.
I think, I'm not sure I would be so bold as to consider it 3.0, but maybe like 2.5 is the same as 2.0, but with an extremely large amount of transfer learning. So basically, the whole thing about GPT-3 and fine-tuning it or prompting it to do a particular task, I would say that like that's my expectation that within computer vision, as we are already in NLP, within computer vision, we'll also get closer to that where you have this like large, generically pre-trained model, which is like decently good at many tasks, and all you have to do is fine-tune it on a small amount of your own data. That's actually kind of what I'm like, I assumed would exist already, or like this, I don't understand why it isn't there already. And we're actually kind of getting there. There's been recent papers on, I think from Google on image transformers and like applying kind of the same approach to computer vision as with the GPT-3. So that would be my answer. And 3.0, I don't know. I can't think that far. I think 2.0 is already like, we're making the very first steps towards that. Like Tesa is doing that. I know, like Starship is doing that. So few companies are doing that, but it's not. It's definitely in the very, very early stages.
Thanks. I'd like to maybe focus a bit more on this transfer learning part. Because I guess, yeah, like if you're collecting your data sets, it's quite likely that maybe there's an open data set that can cover some aspects of that, where somebody has already trained the models. You could kind of use that to predict your data set and then kind of just start refining the labels that you already got from an existing model. So do you think that's kind of a feasible approach?
It is again in the category of things that should exist but doesn't reliably. I recently had this Twitter thread where I was like enumerating things which are normal in the software 1.0 world, like developer tools basically, and which are totally missing in the data science world. And one such thing is dependency management. Like you want to potentially be able to say like, I want to like inherit from a model that has been pre-trained on XYZ datasets, or I want to like start off from I want the starting point of my model be like something that has been trained on a particular dataset. So you have some sort of dependency graph coming out of the like dataset dependency graph, and this I think would be the best. Like again, it's not something that is technically infeasible. Like it would be possible today, but it doesn't exist as far as I know. Maybe it's like a niche use case, but I would definitely like to see that.
Actually, that kind of led me to a connection. There's a kind of like going back to kind of what I kind of showed in my introduction. Like at this stage, we are working in a relatively small data set of like 27,000 samples, and I mean we do this basically kind of similar things of projecting it into 2 dimensions. In biology, we don't use like we usually use things. Well, UMAP and Disney are new things that people started to use. Most of the times, PCA is fine. But kind of, I think we're kind of at this stage we're like somewhere where we're kind of we have human assigned labels and we're happy and everything works. And then now we're kind of there are new data being generated, which is like where you measure single cells from individuals at a time, and then you no longer can manually label them because the latest kind of data set came out. They have 4 million cells, but basically you have these 4 million entities in some kind of vector space, and then you kind of want to assign them labels. Are they immune cells? Are they brain kind of neurons? Are they something else? And then there's like a couple of hundred different data sets that have been generated, and you know that there's some overlap. And then you want to kind of be able to translate labels from one to another. And I think there's definitely kind of, the methods are not there, but I think there might be kind of nice overlap between like what we are trying to do in these kind of biological cells, mapping them to each other to images, which are also kind of represented in a vector space.
Yeah, well, one way of transferring is basically what I showed before, where you take the embeddings from one model and use that to explore the data set. The thing I would like to see, I forget what I was saying, something about the data set of like transferring the data sets, individual cells. I don't know. Anyway,
like I guess eventually we would like to be kind of. I think one of the things that we are struggling with is that there's kind of you have these same biological, like we have biological entities. You have coins or stamps, yeah. But then like if I collect my sample of images of coins, they will be systematically different. So there's kind of some kind of like patch difference from my set to what the other data set used. Yeah. To kind of be able to ignore that and kind of be able to distill that these are coins and these are stamps from kind of this like this old famous example of distinguishing tanks from like background where all of the tank photos were made in summer, which is.
Yeah, I think there's a huge amount of waste going on because if you don't transfer it, you basically learn from scratch all of the basic image filters. You learn all of the intermediate representations up to the very high level concept of like what kind of cell it exactly is. So I'm not even sure why transfer learning is not more popular. Maybe it's like there's no good papers that can come out of this, and it's more like a hack that people don't like. I don't know. It's difficult to tell. But for me, the way I think about this is that so the slide I showed before of the obvious coins or the 8 obvious coins, which like you can outsource. the whole premise actually is wrong. Like you shouldn't even have to label obvious examples. Like you should label one of those, but you shouldn't have to label 10,000 obvious coins. And for me, like if you think about the physical limit, like the lower bound of how quickly can you teach an AI, or like how quickly can you teach a task basically to a machine, then the lower bound is the number of samples that it takes to define the decision boundary to within the accuracy or the performance that you require, times the milliseconds it takes for a human to judge like the information that as it enters their like retina up to the point where the judgment is made in their brain. Like everything else is wasted time on waiting, bad interfaces, bad learning, wasted time on like lack of transfer. So this should be for me, this is the standard. And when I speak about building good data sets quickly should mean, like for the coin data set, it should mean like 30 seconds. It shouldn't be that you have to label data sets for like several days or weeks even. It should be like on the order of seconds. If you do this calculation, it's like 100 examples times like 200 milliseconds, 20 seconds, right?
Yeah, I completely agree. I think that's something like I personally feel with most of the data that I'm interacting with is like I can make this judgment really quickly, and then kind of transferring this into some kind of annotation that's actually usable is a huge pain point.
So I think this comes because we focus on very good software. Like we have very good tools for training models, like TensorFlow is a superb package. We have really bad tools for going through data and building annotations. Like people are kind of working on that, and companies are building that. But if you compare again, like how good tools we have for building software, like an IDE, linters, compilers, test suites, like all of these tools, logging, monitoring, alerting, and comparing that to the data scientist's toolkit, which typically is like Jupyter Notebook plus looking through images on your local disk, then it's kind of sad to see that, and I would like to fix that. I'm trying.
Thanks. There's one question here is data compiler an actual technology or a concept? If this is a concept, then what way does it differ from regular data quality techniques, like for example, data cleaning?
I mean, it's a concept which has actual implementations already, like I showed, like so the Uber Ludwig, many online or like commercial tools, or you can write. Basically, you could easily write the script which, like, given properly formatted source images, trains a model into and dumps it into a properly formatted output. Like it should be. It is very simple to do that. Again, using Keras or some very high-level interface. So this exists already. I think few people explicitly think about it that way, but in principle they exist. Not just not explicitly as the goal is not taken as building a compiler for image classification or for neural networks. It's very different from I don't know, data classification, data cleaning. Data cleaning is a process of going through an original data source and somehow transforming it over time with different actions into a cleaner data set or somehow better data set. And the compiler's purpose is to take a data set and turn it into an output binary or a program, basically. One thing, I think there is one commonality actually, is if the compiler tells you if the code doesn't compile, but the neural network training code does not tell you when the data set is garbage. And this is kind of what's missing in the software 2.0 world. It's one of the many things that's missing. And actually, I think to some extent this could be done. You could be easily warned about this image is just black pixels, or you have extreme class imbalance. You need to do something about it. Or there's this simpler things we could catch, but actually I think this is what makes machine learning difficult. It's difficult to automatically catch data bugs.
Thanks. We have a 2-minute break. We'll be back here or maybe actually it's more 30-second break, and then we'll be back here for the panel discussion. We can start. So I prepared some questions before the seminar, before I had seen any of your talks. So some of them are good, but most of them are mediocre, I think. So if there are important things that you feel that we should discuss, or I think if there are also questions from the audience, you can put them in the chat and I can ask them. But I'll start with something and then we'll see where it goes. So what do you think is a bigger challenge right now? Handling large data sets, or versus annotating and curating these data sets, like the data volume, or kind of managing the data volume versus managing the data annotations. I feel there might be different opinions depending on what people work on. So yeah, Łukasz, maybe you want to start.
I have to deal with data annotation, so I have no opinion about it, actually. So I don't know how to answer your questions, actually. I think I'm missing a part of the spectrum here to have a full picture and answer this question. Maybe I will leave it for someone who has actually had some experience to work with both sides of it.
Oh, that's you.
No, it's not actually.
I think I've spent more time on the labeling part, but I think I haven't, like, data infrastructure as like the sort that Łukasz works on. It hasn't been really the problem I have been I have had to worry about. This has been solved by another team. The infrastructure that I have had to worry about is like all the tools and processes, like the tools supporting the processes around data labeling. I don't know, like, how do you manage tasks between people? How do you do quality control? And they're not necessarily technically complex, and maybe they are at large scale. But like this part, I would call it like dataset tools engineering or something like that, which is to some extent it's related, because you still need to, like, I don't know, get the large amount of predictions in a timely manner from one system to another. It's slightly related, but I think in this system, usually, like, the standard solutions are relatively easy compared to the other problems. So maybe it's even that they're different worlds, like reporting to different teams, different people, as we can see here. Right?
Yeah, kind of same feeling about that. I haven't had to personally really worry about that side of things that much. There are other people who work on the data engineering solutions. The fact that I haven't had to worry about them, I guess it's good, just a good testament to how good these people are. so yeah, so I'm a bit biased.
Yeah, it seems that maybe the problem that you're currently dealing with seems to be the hardest one all the time. Like, from my current perspective, I see that annotated data is clearly a larger problem, because I see that we are gathering and handling the large data sets. We know how to do this, but nobody has ever thought that, okay, when we want to do like predictive models, then we need labels. And since there are no labels, then this is a big challenge. But at the same time, that said, as I mentioned in my talk as well, that when we, for example, want to gather the very high frequency or high resolution data from smart meters, which hasn't exactly meant for that specific purpose, then we might run into the problems that are like almost seem to be impossible to solve. For example, even the communication technology just doesn't enable such a frequent data gathering yet, for example. So like for data annotation, I feel that, okay, this is also like, this is a problem, but I see how to solve it. But from another perspective, with some data gathering parts, there might be even problems that you can't even solve with current technologies.
Thanks. So, kind of, tell me if I'm completely wrong, but like one of the kind of aspects that to me feels that it's like people get into kind of like the people who get into data science and data engineering, they are very much about kind of building complex systems, and so building these kind of data management pipelines is very complex, and we've done kind of some of work our own as well. It's quite complex, but it's a known unknown in a sense that we know how to solve it, or if we don't know how to solve it, we know who to pay to get it solved. But then kind of this data set engineering is like we're kind of getting this problem where we have to solve problems that we never really wanted to solve.
Perhaps put it this way, that data engineering in general is just like a bit more mature than like in general labeling or just overall the dataset game or the dataset domain field, as I describe it, like the labeling and giving examples. So it's data engineering is more mature, and I think it's one example or one like metric for that is what scale can be handled by state-of-the-art tools. So like Łukasz described that some of the tools that are basically off the shelf, or like Amazon offers them, to anyone, support petabytes of data probably. If you look at typical labeling tools, most of them, like they're designed for workflows up to like 1 million images or maybe a couple more, but no one is offering a solution where you have like 100 billion images and you want to like build a good workflow around labeling those. So I think that's one way to measure the maturity, like what scale can it support even.
Even tools at the level of millions are few and far between. Like most are tens of thousands or thousands.
Yeah, and like looking through images locally, like 100K is roughly where it.
Well, also what I can add here is actually often there are a lot of marketing traps. So there is a high throughput, or you have like perfect technology for one thing, but like very often you have like a list of the features that it offers. But one thing that they never tell you, it's like you cannot have everything at the same time. So probably that's the biggest limitation here.
So you can either save the data or have it in a database.
You can save it in petabytes, but like there's like small asterisks, probably like you have to be like in some certain format, or you have to be very rich to pay for it, There are some
systems fast and reliable, but not at the same time.
Exactly.
So another question that I think like topic that came through here is like data quality issues and the need for like being kind of that only kind of I guess like only you can charge data quality if you know what the business case is, and so kind of. Or maybe I'm kind of overinterpreting it, but kind of like, what is your kind of experience I mean, this is like starting from like purely data engineering side to kind of more like dataset side is like, what is kind of the relative importance of like the domain knowledge of the field? Like you mentioned these QC rules that you have to come up with versus kind of technical skills of handling the data.
I think like everything has to be connected. From my experience, like if you just give data engineers like, hey, there's a data set in some from some source that you have to like, I don't know, synchronize or put it available for querying. There is like, okay, there is a data, we convert it, that's it. But like it can be garbage data. So always there has to be some cooperation with people from like kind of more product side, data analysts, data scientists, the consumers of the data, who will define what is the good quality of this data. And yeah, I think it's like,
how do you communicate that? Like how does this communication work in your team? If the user detects an issue with data quality, how does this lead into improvement in data quality?
Oh, this is a very tricky question. How can I answer it in a polite way? Yeah, always it's kind of ping pong with between different teams, between the producers of the data, their final consumers, and data engineering somewhere in between. So yeah, if you have your organization, you can define proper processes into it. But yeah, I think it's always like a matter of many iterations to going like sometimes you just add the data source and everything is perfect. So there's no even need to kind of validate it. So I think it depends from case to case. One thing that is very important, I think, with the data validation is that I've never heard it like people talking about it, but data quality is extremely expensive to validate it, especially from the final point of view. So if you have huge amounts of data and you want to run some periodic checks and make sure that, okay, all this data as a whole is correct, it has colleague values and so on, it can be really, really expensive. So what we discovered is that I would say the most optimal way is to do it when you incrementally add the new data to the data set. So checking those smaller deltas of data that you add, the updates, and that's what makes it kind of manageable in a scale.
one aspect of, so I think when I speak about data quality, I mean label quality as opposed to like completeness or correctness or, like statistical properties actually corresponding, which is a kind of a test of quality. So label quality as in, you can measure it maybe as like what percentage of the time does the label in your like annotated data set correspond to what you would want it to be. So let me unpack that. The whole notion or the definition of data quality I just gave assumes an oracle. Like there is an oracle that can tell you for any data point what would be the correct label, and there is no oracle. Like there never is an oracle. Like I explained to you right now, there are judgment calls that need to be made. At any organization, you need to make those judgment calls. Someone needs to make those. It's a person, it's like a group of people, it's a process, it doesn't matter. There needs to be an oracle, and you realize that you can never really get perfect with this oracle. And even if the oracle exists as a process, you can't apply it on every data point. If it's like 4 people getting together in a meeting and discussing the photo, then it's quite expensive and you can't use it on like 10,000 or 100,000 images. So I think a better concept for thinking about label quality is alignment. So there's some, like the oracle would implement a particular policy, and I, as a labeler, I am aligning to that policy. How well am I doing that? Like what percentage of the time am I aligning to the policy? Or some other person, how well are they aligning to the policy? How well is the model that has been trained aligning to the policy? So I think that's just like a better word to use, because it removes the notion of like ground truth, perfect ground truth existing. So alignment is like, you can also measure alignment between like how well I am annotating and how well Rao is annotating, or what my opinion is versus what another person's opinion is. And it gets quite complex, and especially explaining it, like to people who don't work with it day to day, they ask like, okay, but like what's the accuracy of the system? And like, okay, but against what policy or against what standard? And like the point at which you start to understand the difficulty of that question is when you start looking through these examples, like, okay, you tell me what the pile of coins is like it's supposed to be. And the hard part is that you can come up with an answer internally in the organization, but when you serve clients, they also have an opinion on that. And especially at Tartu, like they are legally bound to that opinion often. So they have like a legal responsibility to the regulator to actually do things in a particular way. So they may have a really strong opinion that like a pile of coins is never a coin. It can't be a coin. It shouldn't be a coin, and it's illegal for it to be a coin. And this just makes things so much more so annoying. It's not just like a simple, you just label the data. It's not like the first step in the process to do it is done. It's so much more complex. And one like small maybe argument of authority, I think on data quality, when he was giving the concept, the same seminar, I think a couple of years ago, he said that most of his time goes into how to label, not how to like what neural network to pick. Maybe I'm exaggerating, but it feels like even interns work on the like picking architectures, and, like, and then like the top people think about how to label things.
Yeah, one thing that I would like to point out is that the whole notion of data quality is probably, it can be considered only in the context of the use case, as you kind of mentioned as well. That I see that. If you look at some use case that currently exists, then the data might be like excellent quality. But if we start considering the use cases what the manager wants to see in 1 year or 2 years, then the data might not be so high quality anymore. So this is like one notion that I personally have pushed in last year in Eesti Energia as well, that our data governance process should start to consider what manager wants in 2 years as well, not just like what manager asks them today.
Expanding on that a little bit, like both of you touched on this a bit, but the data quality is like directly correlated to the performance criteria that you have, right? And that can vary wildly based on what your goal is and what your system is. Like there's a cost to a false positive and there's a cost to a false negative, and that cost can be very different depending on what you're building. And based on that cost, that's the threshold for what your data quality is. Right? If you can never have a false negative, you're investing a lot of money, time, and energy into making sure that there's never a single false data point in a data set of like 10,000 data points. Right? If you just have to have correct answers more than incorrect answers, then you can be pretty loose, right? Like it's more or less working.
I would actually love to be in a situation where you like perfectly know, or even approximately know, the false positive versus false negative cost. Because this is thinking my first question when I'm trying to rate, like how much does a false positive cost, how much a false negative cost, and up to this point, it is an ongoing discussion, like what the relative weight should be. And I think only recently, like we got to a point where we have like a very good framework for thinking about like how to weight different areas. And it's really difficult to come up with something like that. And it's very, very domain specific or problem specific as well.
I think that's like you had a very clear idea of like how much would have like a false positive cost in preventive maintenance. You knew how much like you could save money potentially. So it's you were in a very good place in that sense.
I have actually I feel that in our field there are several other cases that we are working with where the false positive, false negative cost can be kind of well defined. Because in some cases, well, there are some other use cases where our like false negative might mean that something breaks down, but false positive just means that someone is double checking something that wasn't meant to be checked.
One thing that's I think funny to think about, or maybe morbid, depends on how you look at it, that regardless of what they say, self-driving car companies must have some utility function which ranks the value of a human life versus like braking too often. Like it must be there. Maybe it's one weight is infinite, but there needs to be some sort of trade-off. Otherwise, the system could not operate.
If it's infinite, then it actually also can't operate.
That's true. Yeah, right. Maybe like it's like millions of times higher or something. But but it's it has to be somehow in there. It has to be for it to operate. And whether it's explicit or implicit, I think like I would rather have like society make this difficult discussion once, and then we could argue about it, and then it would be like maybe a common decision or at least a range, or it would be somehow more transparent. I guess maybe that is something that will make people trust the decision making more. I know I'm actually like maybe it's distracting because they're so much more safe than like normal drivers that it's could be like the weight is completely on the braking, right?
So like maybe moving to a slightly different topic in the annotation side is one of the things we do in biology is we kind of I've basically learned in like the past year is that there are lots of people thinking about ontologies. And so like basically like you have some objects and but then you can kind of like in image sense you could have like a bounding box of like a traffic light, but you could think that the actual label could evolve over time in a sense that you have a bounded box of like a traffic light, but then it might be that maybe later you kind of it belongs to one ontology, and maybe in some images you would kind of move it to a different branch of ontology, like traffic light versus a subtype of a traffic light or something like this, which at some level you would only care if it's a traffic light, and in some other cases you would care it's a specific subtype of traffic light, but it would be maybe useful to maintain this relationship. Does this exist?
It's super difficult, I would say. As well.
Yeah, I mean, I think it conceptually exists. I think it exists in our systems as well. It's a question of how explicitly it exists, right? Mm-hmm. And I think it's super difficult to sort of explicitly define this, especially if you have like an evolving system as well. So yeah, it's a tricky thing to handle.
And like the simplest question is like, if you try to distinguish between like a minivan and a van, should it be a different class or a property on the same class?
Yeah,
and this will kind of affect, maybe it will not affect how you train the model, it will slightly affect like what sorts of analysis you can make. Maybe it's just like a small database implementation issue, but it already impacts like how you query it, how easy it is to use. And in some cases, it impacts what you train or what the goal is. If you separate it into different classes, it will be maybe more difficult or easier to learn for the model. And I think for me, the best solution has been, or the kind of what I'm promoting as well, go through a lot of data before like arriving at an ontology or going into like a large scale labeling effort, because that way you can kind of figure it out.
Yeah, and of course you're maybe touching the area of representing the data or representing the labels maybe in some graph form, then that you can kind of deduct these from there. But also actually one aspect that I wanted to point out when Taivo mentioned this software 2.5 idea, that in recent 2 years I personally been researched a lot reinforcement learning, and there I see that one thing that needs to happen in some time or something is that how to represent an observation in very compact embedding. And I mean that like in a way, if we say that software 2.0 is a dataset, good quality dataset, then maybe software 3.0 or the source code 3.0 could be like a very compact embedding of the observation, which includes also information which is not maybe kind of even like seen directly from this observation, but includes some relations to other like concepts or something like this.
Context, you mean?
Yeah.
Thanks. One of the things I thought about is that there is some question. I see. Maybe I can open it here as well. I can't really see it, but there. So there's a question about Estonian AI strategy. Have you thought about it? Do you actually know what it is? I don't.
I was part of the working group that was. I would let me re-represent that in a way that makes it more accurate. I was technically part of it and sometimes gave feedback to parts of it. I was not like a core part of it. It was mostly different government agencies working together, driven by the Ministry of like Mines, Communication, Ministry of like Economics and Communications. I think it is like not common yet for most countries to have an AI strategy, or at that time it wasn't very common. And the projects, I think like I would evaluate it on top of or based on the projects that have come out of it, or the things that have actually been kicked off. And I think some of the things which, if I'm correct, I think like have actually come out from that, or after that at least, like initiatives to build common libraries, or either common datasets or common libraries for machine learning models, like let's say common corpus for Estonian speech recognition, or common model even that could be embedded into different applications. And this strikes me as a very good idea because especially like you can imagine a world where Amazon says that we will support any language as long as there is a dataset with like X properties in X format, and then every government could just like sponsor building such a dataset to get support for their own language. And this is kind of like the first step towards that. And I think it's good. There's a lot of initiatives in like policy, in education, etc. But I'm not like very, I haven't deeply gone into them.
Okay, so I'll have one final question to finish the discussion. What do you think will be the key revolutionary changes in data and dataset engineering in the next 5 years? Like, what do you kind of? I mean, the 5 is an arbitrary point, but what do you think? Like, you think it's such a pain point that it must be solved?
I will go back to their representation learning, the learning to represent things in very compact way.
Yeah, I guess I could build on top of that is if you learn a very good representation and you can do it based off of large data sets without labels, then it makes it much like kind of the definition, or part of the definition of a good representation for me is that it's easy to learn or transfer that representation. So I think that's at least in applications, I'm not sure that has been super well explored right now. Maybe in academia, but I'm not. I haven't seen like great applications of transfer.
Not just repeating, but maybe adding to that, I think the other part is the development of the ecosystem as well. Like not necessarily huge technological or research advancements in how we do handle these types of things, but having a more mature ecosystem of processes and tools. So if I'm starting a company that's hugely data dependent and building a new product, then it's not a question of, oh, I should figure out how should I organize my data processing and the data labeling and everything else. But it's a question of, okay, this company and these companies offer these tools, these work, we'll do this. And I think that's hopefully what's going to happen in the next 3 years.
Like a default stack.
Yeah.
I think also, if I have to add something to it, I would say that standardization and maybe some high-level frameworks to improve data engineering in a way that you just need to have some descriptive language to define your pipelines, like what kind of transformations you want to have. And then this thing can be applied to any stack that you use. So it's either like AWS, either it's Google, or either it's like your on-premise deployment or of the stack. So if I have to translate into the software development or SRE nomenclature, it will be like some kind of Terraform, if you know the tool for building the infrastructure, but adapted for building the data pipelines.
So I think it's a very good point to end on. That's what we're trying with biological data as well. It's kind of to develop data processing workflows that we could run on different locations and they would actually work. Especially if you're not allowed to take data out, like you have clinical data that you can't take out, then you want to take data pipeline to the data and execute their kind of efforts to develop standards. But we're still quite far away to kind of make it actually seamless. So I think it's a good point to kind of end on. We need more standards. You know the XKCD comic. So with that, I think we'll end today's seminar. The next seminar will be on the 28th of January, and the topic will be using data science in business.